Assalamualaikum and a very good day everyone. Today my group 6E will be presenting our IDP project. So for my part, introduction principles of chemical engineering. Principles of chemical engineering is a 3 credit hour course designed as a fundamental part of the Bachelor of Chemical Engineering with honors program at University Technology Petronas. This course introduces us to the basic principles of chemical engineering and help us understand the overall chemical industry, problem-solving methods, and key calculations needed in this field. Chemical Engineering Fluid Mechanics is a 3 credit hour course offered in the Bachelor of Chemical Engineering with honors program at University Technology Petronas. This course is one of the most important components of the body of knowledge for a chemical engineering student. Chemical Engineering Fluid Mechanics is a 3 credit hour course offered in the Bachelor of Chemical Engineering with honors program at University Technology Petronas.
Hello, I am Ahmad Farid bin Saidaza and I will present to you the process flow diagram. So the process begins with introducing the feed stream including isopropyl alcohol and water along with air and natural gas at an initial temperature 37 degrees C and pressure of 1 atm. This stream undergo preheating in the reactor furnace increasing their temperature before entering the vaporizer where the liquid phase is converted into vapor at 370 degrees C and 1 atm. The vaporized mixture then moves into the reactor where the primary chemical reaction takes place under condition 310 degrees C and 2 atm. After the reaction, the hot reaction mixture is passed through a cooler, bringing its temperature down to 40 degrees C and 1 atm. This cool stream then enters a phase separator where the liquid and gas phase are separated. The gas phase is directed to a scrubber where impurities and unwanted components are removed. Meanwhile, the liquid phase proceeds to the distillation column where further separation of components occur, resulting in the production of acetone. So the acetone is collected and stored in the storage tank, while off gas and water waste are moved as byproduct. Throughout the process, temperature and pressure conditions are carefully controlled to ensure efficient separation and reaction.
Hello, my name is Muhammad Dan Shaikal and now I'll be continuing on the function for each unit operation. Firstly, vaporizer, the function is to heat IPA to vaporize it by ensuring a uniform fit for the reactor. Secondly, the reactor function to convert IPA to acetone and hydrogen under controlled condition. Thirdly, reactive furnace, the function is to generate high temperature heat via combustion and transfer it by molten salt. Next, cooler, the function is to lower reactor effluent temperature for effective phase separation. And next, we have phase separated, which is the function to split the effluent into gas and liquid phases for further processing. Then we have scrubber, the function is to absorb residual acetone from the gas using processed water. And then we have distillation column, the function is to separate acetone, IPA and water through the vapor liquid cycles. And lastly, the storage tank's function is to safely store purified acetone under controlled condition.
So now, we're going to talk about mass balance for non-reactive system calculation. We have did the flow diagram with a few information in it, but we still need to find 4 unknowns. First thing, we did the degree of freedom, which is unknown minus independent equation, which is 4 minus 4 equals to 0. This means that this question is solvable. And then we showed that there's 4 equation which is 1 for overall equation and 3 from specific equations. So next, from the flow diagram, you can see that the top product is in metric ton per year. So we need to change it to gram per hour. To find the molar flow rate of the top product, we need to find the molar flow rate of each component in the top product, and then sum all the molar flow rate in each component to get the molar flow rate of the top products, and then use the equation that we did before to solve this equation. And then at last, we will find the 4 unknowns, which is N1, N2, Y, and Z. We did the calculation for non-reactive system. So for now, we're going to do the mass balance for reactive system calculation. First, we did the flow diagram, and then we have to do the chemical equation for 2 equations, which is complete combustion equation and partial combustion equation. And we continue to do this calculation using element balance method. Next, from the element balance method that we use, we can finally found the amount of air supplied to the reactor and percentage of excess air supplied.
So I'm going to perform the energy balance for non-reactive system. So we take the distillation column for this non-reactive system. And from the table, we list out all the components and we take the data that has been calculated from the mass balance. So next, we take the 37 Celsius and 1 atm as a reference state. And for example, if right now we want to calculate the enthalpy 4, so we must know the boiling point of it as is in the vapor state. So it must be got enthalpy change from 37 Celsius to 56 Celsius, and then we need to plus the heat of vaporization, and then plus the heat that changed from 56 Celsius to 60 Celsius. And then after that, when we sum up it, we can get the total of the enthalpy change for H4. And after that, when we calculate other enthalpy change in the same way, so that we can know that the heat transfer is also equal to the enthalpy change. So the enthalpy change is N out, H out minus N in, H in. So when we minus it, we can get the final answer for the enthalpy change. So next, for reactive system, we use the conversion of methane for this system. So we got two reactions for this system, which is the complete combustion and incomplete combustion. So first we list out all the components involved and the data given, and we take the reference state as the 310 Celsius and 2 atm. So for example, if right now we want to calculate the enthalpy change for H9 and it got the pressure difference, so we do use the formula V delta P. And after that, we do calculate the enthalpy change from the 310 Kelvin to 317 Kelvin. And when we sum up it, we can get the answer for the H9. To calculate the standard heat of reaction for it by using the VH product minus VH reactants. And after we calculate all the things, we can calculate the enthalpy change for it, which is using the extra of reaction times the standard heat of reaction and plus N out, H out minus H in and in.
So here's the pipeline layout. From the slide before, you can see the flow chart of the pipeline, and that consists of pipe 1 to pipe 15. And here you can see the connection of the stream. And then the type pipe that we use is stainless steel pipe because that is the most effective pipe to use in the acetone production. And for the diameters, all the pipe is 5 inches diameters. And then for the fittings, there are two fittings, which is 90 degrees standard elbow and standard T flow to run. And then we also include assumption and pressure drop contributions.
So now I will continue on the calculation of pressure drop for the pipe layout. First, to calculate this, we need to apply the energy balance equation and find its pressure difference. Firstly, for pipe 1, first we need to find the total friction loss because later we will apply it in the energy equation. In order to get this value, we need to find a Reynolds number first to determine whether the flow is turbulent or laminar. To find the velocity, to calculate the Reynolds number is by using the volumetric flow rate formula. Volumetric flow rate formula can be obtained by converting the molar flow rate of 100 kmol per hour as shown in the pipeline layout design. That is, then it will be divided by the surface area of the pipe and we will get its velocity. Then apply all the value of assumption and reference to Reynolds number into the formula to get its Reynolds number value. As soon as we identify the type of flow of the pipe, you will get to know what formula to use to find its friction factor. Using the friction factor value we just calculate, apply it in the total friction loss formula, and also by considering all the loss coefficient. For example, in this pipe 1, coefficient of loss only involve the enlargement and contraction of the pipe. Then the total friction loss we get for pipe 1 is 0.02759 joule per kilogram. Applying this value to energy equation by also considering there is no work, no elevation and change of velocity, we will finally get the pressure drop for pipe 1, which is negative 21.65 Pascal. Then this calculation for pressure drop will be applied across all pipelines with changing of its pipe condition and situation like density, flow rate and fittings. The table in the slides shows all the pressure drop calculated for each pipeline.
Along the pipe, I use the same calculation method for all the pipes in the system up to pipe 15, applying their respective mass flow rate based on the process flow diagram. This ensures that every section of the system is analyzed for pressure drop consistently.
Hello guys, I'm again, and right now I will explain to you guys the strategies that we use to deliver acetone to a storage tank. So the first strategy that we use is we optimize the pipeline design. So we chose the material that highly resistant to a corrosion, which is stainless steel. So apart from that, stainless steel also give us the durability when handling acetone. Moving on to the second point, which is minimizing the friction losses. So we take an account for pressure drop due to the pipeline, elevations, change, and fitting. So fitting that we have is 290 degrees standard elbows. And moving to the last point, which is we use pump assisted transfer. So we choose centrifugal pump to ensure steady and continuous flow of acetone, particularly to overcome the 5 meter elevation difference between the column and the storage tank. So this pump help prevent cavitation, and ensure smooth operation while maintaining energy efficiency. So now we are calculating for the pump power. To calculate the pump power, we use energy balance equation. We assume this it is steady flow of acetone, which is the velocity is the same. We also assume the pressure difference of the at the end of the pipe is 135 kilopascal, and we just sum the value into the equation, and we got the ideal work done by the pump is 1 to 1.81 joule per kilogram. So now we assume the efficiency of the pump is 65%, so we can get the actual work done by the pump. So we use the formula actual pump power equal to the mass flow rate times with the actual work done by the pump, and we just sum the value into it, and we got 21.598 times 10 power of 6 joule per day, and so it means that 21.598 times 10 power of 6 joule of energy needed in order for the pump to operate in delivering the acetone in one day. So now we are calculating for dimension and capacity of the storage tank. So as we know, the velocity of the flow is 0.13067 meter per second, and we apply the continuity equation Q equal to AB to get 145.89 meter cube per day. So we need to convert it into liter. So it is equivalent to 145,890 liter per day. So as we know, we need the volume of tank greater than volume of acetone supply per day. So therefore, we take 200,000 liter for the volume of tank. So now we need to find the dimension. So we assume that our tank is cylinder. So we use the formula of V equal to pi r square h, and we take the radius of the cylinder to be 2.5 meter and calculated it to found that our height is 10.19 meter in height. So that's
So in conclusion, fluid mechanics plays a significant role in designing the plant's fluid handling system by addressing the key aspects such as the flow behavior, pressure drop, and pump selection. And what's more is that principle of chemical engineering also guides the design of the essential unit operation. So we need to integrate the fluid mechanics with the principle of chemical engineering to ensure that our plant design is efficient, safe, and sustainable. So safety is also a fundamental aspect of the design process, so we need to consider it to mitigate any potential hazard. So in conclusion, designing an acetone production plant demands a multidisciplinary approach that leverages the fluid mechanics and principle of chemical engineering. So that's all from our group. Thank you.